Hi, recorded is rolling. It is Monday, August 26th. Okay, so coming back from the weekend. I need to give you guys a recap from back last week. You guys were rolling cars down inclines on Thursday, and we made a bunch of graphs on Friday. That was a setup for this linear motion today. Okay. A lot of times I like to, if I can, start new topics with labs, which we did this time. Okay? So that you can get your hands on materials and get measurements and observations. And then when I give you equations later and other stories, you say, oh yeah, that connects exactly back to the labs we were doing. Right? All right, I have some videos for you guys with Paul Hewitt. He's going to take you guys through linear motion, and drive a few little equations. You guys think about things like, remember, you're trying to figure out what's the, throw the questions up here. What's the relationships between, say, like, how far is the car rolled and how much time and how fast is it moving at the end? Right? Maybe questions like that. Right. Um, right. We'll do, I have posters for you guys. So you guys remember our very first day of school, you walk in, I gave you guys these thumbnail notes. All right, so we're moving past the silver banners and on the back side of these red banners. I'm going to get started on these by the end of class. So we're working towards that. Okay. Yeah, we won't quite have time to fully drive these today, but Paul Hewitt will start walking, get you guys simplified versions of these. Right? Same thing as your lab. Right? And then, ooh, yeah, this note here. There is testing tomorrow for 9th and 10th graders. I know I have a few 10th graders in each class, right? So heads up there. I think I told you where you're supposed to go if you are. I think what I'm going to do, there's not supposed to be testing in this room. So I think what I'm going to do is just, because I have like, maybe like 2 or 3 10th graders per class, is just go ahead and keep teaching the lesson. And then if you are in 10th grade, then you'll just have to catch the video, right? See what we did in class. If you think you're testing tomorrow, but you don't know where, let me know at the end of class and I have an Excel page I can look it up for you. Right? All right. So you guys good so far? Everybody good? All right. So, okay, let me, let's do a recap because I know it's been a few days. It's been a few days. All right. So we're trying to figure out what's the equations governing the motion of the car rolling down the incline. And I had to split you guys up into different groups right? Because there were so many variables I had to juggle, right? So I had to control some and let some be independent or dependent. We were able to come up with graphs for these type relationships, right? So let's do some of these. Oh, pause this here. All right, record and resume. All right, so here, I'm just gonna flash a couple up here. Right? So one idea was how fast is the car going as a function of time. Right? So you guys had stopwatches, time, and some of you guys had speed gates. The car was going through the speed gates. Right? What you guys found was that there was a direct relationship. And what that means is if the car rolled some time, okay, it picked up to some speed. But if it rolled for double the time, it picked up to double the speed. And triple the time was like triple the speed. You guys remember that? Right? So you'll see that later. Right? And then another relationship, this one is a little trickier, is you guys measured distance and time. Right? So how much time had passed. Let's this one left, right? Then how far did the car roll? Right? Now that one was what shape is that? Not a line, not a parabola, right? Yeah, you guys remember that too, right? And we did this little linearization trick where it's like, well, okay, if we suspected parabola, we can square the time, put that on this new axis, and then do x versus t squared. Now that did linearize, and then we could get the slope and come up with an equation. Oh, look, guys, it's the same equation. Is that equation that equation? It's the same thing, right? X is something times time squared. Interesting, right? Okay, so what does this mean? Well, proportionally, this means if the car was rolling for some time, okay, now it's gone some distance. If it's rolled for double the time, guys, that's how many times the distance? What's a factor of 2 squared? It'd be 4, wouldn't it? So 4 times the distance. What if it was 3 times the amount of time? Now that's how many times the distance? What's 3 times the time squared? It's 9 times the distance. Remember that? Right. All right, so yeah, we'll come up with more formal equations for these, but let's flip over to Paul Hewitt. Oh, I remember what I was going to say about Paul Hewitt also was, right, as I'm recording this video right now, because I'm recording right now, right? A lot of times when I record this, if I play videos, the audio does not play. I don't know, I think it might be a copyright thing they try to do. So you guys know all these Paul Hewitt videos are uploaded already to Google Classroom and a couple of zip drives. All right, so think about what that means. I think you guys can visualize this. So you're in your car, right? You slam on the gas pedal, you're speeding up. You guys can feel it. You feel thrown back and see, whoa, speeding up. Okay. Can you guys see the speedometer needle moving? Right. How many miles per hour is it picking up every second? 6. Yeah. Yeah, it's picking up 6 miles per hour every second. You see it? Okay. What if you slam the gas harder? Could that needle move faster? Okay, so acceleration has something to do with the rate that needle's moving. Okay. What about this? What if you're driving cruise control? You're just constant velocity on I-95, just constant velocity. Is that needle moving at all? No. So do you have speed? Yeah, you have speed. Maybe you're going like 70 miles an hour. But do you have acceleration? No, because there's no change, right? So what's the rate that the needle's moving? Now, how about this? Oh, guys, look at these units. Miles per hour per second. All right. We're almost never going to use miles in this class. You guys know we're going to stick to metric, right? Also, look at this. Hours. Ooh, could that quantify time? Seconds. Could that quantify time too? Ooh, right. Guys, instead of miles per hour, what unit do you think we're using in this class for speed? Not miles per hour, but meters per second, maybe meters per second, right? Maybe last week we used. I think if you had speed gates and you got like 1.2 or something reading it, that could be meters per second, right? Meters per second, right? Oh, and let's go back to this then. What if instead of miles per hour, what if it says meters per second, and then we're dividing that by seconds? So you have meters per second per second. Ooh, do those second units combine? And that gives you meters per what? Second squared, meters per second squared. Okay, guys, you're going to see that unit all over the place in this class, meters per second squared. Anytime you see meters per second squared, think, I know what that means. That means velocity is changing at some rate, and it's telling me exactly the rate that it's changing. It's right. So in this case, I'm picking up so many meters per second per passing second. Oh, he said there's some controls. He's going to name 3. Guys, what's one of them? The what? Okay, so like the gas pedal, right? Okay, yeah. So if you slam the gas pedal, right, you can feel the car lurch forward. Okay, so yeah, that's definitely a change in velocity. That's an acceleration. Okay, what's another thing you can do in the car? The brake, right? Okay, actually, that's the main 2 we're going to care about for about the next couple of weeks: the gas pedal and the brake. Right? There is a third control you have. The what? What else can you do that you can feel? The steering wheel, right? Steering wheel, right? Now we're not going to do steering wheel for a few weeks, but that is true. It's called centripetal acceleration. So hold on to that one. We're not quite ready for that yet, but guys, right? Okay, but guys, this is a really important concept. I really want to hammer this home because I might use this like throughout the year. Right? He said acceleration is something that you can feel. Hey, guys, are we all on a giant spinning Earth right now? Are you about like almost 1,000 miles going straight east? Can you feel that? Can you feel the Earth spinning? I can't. Right? How about this? You guys ever been on a plane ride? Right. So let's say you're just like cruising, constant velocity, way up in the air. Can you feel how fast the plane is going? No. All right. You can feel it like taking off, and you can feel it landing, but you can't if you're just cruise control. It feels like sitting in the room right now. Right? How about this? You're sitting in the passenger seat of a car. Your friend's driving. Right. You in the passenger seat. Say you got a blindfold on. Can you feel? Well, it feels like the car is going about 60 miles an hour right now. Can you feel it? No. Right. You can feel speeding up, slowing down, and turning. All right. I want to see if you guys know this. This may maybe a little bit of trivia. There might be a couple of you guys know this. Does anybody know how much? So you go to the edge of the Grand Canyon, you drop the ball. It's picking up. It's going faster, 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 isn't it? Right. How many meters per second does it pick up every second? Does anybody know? It's between those. All right. It's about 9.8. Every second it picks up another 9.8 meters per second. Right. Hey guys, 9.8 is really, really, really close to what? Nice round number, 10, right? So more often than not, I'll tend to round it to about 10 meters per second every second, okay? Okay. So 10 meters per second per passing second, it's picking up speed. Going 10 meters per second faster every second. And also at the surface of the Earth, right? Okay, now here, I want to switch my screen, do a little recap. So see this title coming up, says free fall, how far, right? Remember, the last few videos, he's been talking about how fast as a function of time. So time's been taken in free fall, right? How fast is it picked up to, right? So that's really similar to this graph from your guys' lab last week. Okay? Of course, you guys were rolling cars down incline. So there's really this right here is actually a slowed down version of pure free fall. Right? Go to the edge of a Grand Canyon, drop a ball, right? It'll pick up speed as a function of time. It looks like the same shape, right? Except this equation will be a little bit different. Right? So okay, so let's do this. So you guys remember this. Edge of a Grand Canyon, drop something, falls down. The speed it picks up to, v, so final could be the end of the interval, okay, is equal to what times time for pure free fall on Earth? What number goes right here? Huh? 10 meters per second squared, right? 10 meters per second squared, right? And then you do a numerical example. You multiply by any number of seconds, and then one of the seconds cancels, and so it leaves you plain meters per second, which describes speed. Okay, you do that, right? Just like that. Right, you guys good? Right. Now, what he's about to do, I got two more Paul Hewitts for you guys. Right. What he's about to do is he's going to switch over and start talking about, well, this right here. Not how fast as a function of time, but how far as a function of time. So back to the edge of the Grand Canyon, you drop something. Right. Now, how far is it falling? Ooh, how far? Right. And that's going to pick up something more about like that parabola type shape. All right. So with that in mind, switch back over and yeah, he's gonna here. Actually, let's go back. We should point out an equation too, because he's going to do a little derivation here. So you guys remember we did two perspectives on the same graph. X versus t, it's a parabola. X versus t squared, that linearizes, right? Neither way is this equation here. You see x equals something times t squared, right? And of course, you guys had an accelerating situation. It's just slowed down because it was a 5-degree incline, right? So you guys get something like this, like 19 centimeters per second squared times t squared, something like that, right? Right, so x is proportional to t squared. What he's going to do is he's going to relate that exactly back to acceleration, because it turns out that this 19 centimeters per second squared turns out to be half the acceleration, right? Now, I think tomorrow I'll be able to derive that sort of graphically in class, but he's going to sort of derive this algebraically, right? So you get to see that, and then you'll get to see a numerical example, and that's these last two videos. Look at the just in time here. Oh, so he's saying distance equals 1/2 gt squared. I guess that. Hey, that sure does look a lot like that formula we derived last week. You guys said, well, we said x, right? So like distance equals, and then something times t squared. Hey, that did look like that format, didn't it? Right. And then going forward into the future, we're going to expand on that a little bit because he did say when he was driving this. Notice this step right here, where he says initial velocity is 0. Right. Now that was true for you guys last week, right? You guys dropped the car from rest, right? So later on, we're gonna add to this and say, well, what if you don't drop it from rest? What if you throw it, right? Then you can add a little bit to this, but otherwise, yeah, release it from rest. It looks like that. All right, numerical example time. All right, here we go. I wonder if you guys can get this before he walks you guys through the answer. Now, he's pointing to that equation. It's boxed in, right? Now, just off screen, it says d equals, like distance equals. Okay, so the distance following equals, okay, and then guys can see the relevant expression that you need, right? So he said it was falling for 5 seconds, right? 5 seconds. Oh, and what was that lowercase g for Earth? How much is that again? 10 meters per second squared. Okay, so that g is 10 meters per second squared. The falling time was 5 seconds. How far did that rock fall? Sorry, you said what? You said 125, right? 125. Check it out. Right, guys, what's 5 squared? 25. Right. What's half of 10? 5. If you have 5 times 25, oh, if you have 5 quarters, how much money is that? $1.25. So put it all together. 5 times 25 is 125. Now also, let's look at units. Let's keep track of units. Time squared. So that could be seconds being squared. And then gravity field was in meters per second squared. Hey, what happens to second squared and second squared? Cancels out. Right? And now that leaves you with meters, which describes a distance. Right? College. So you guys get that? Right? So distance is a function of time, right? Right? So there you go. So now you can solve. All right. So as long as you know the rate is accelerating and free fall on Earth is about 10 meters per second squared, you know how much time it's been falling for, you can solve for any distance it fell. Right? Another question I like to ask is proportional relationships. So it's, if something's been falling for, let's see if you guys remember this. If something's been falling for double the amount of time, that's going to translate to how much further, a factor of what? Guys, double the time. Does that factor of 2 on the time get squared? What's 2 squared? 4. So it should be 4 times the distance, right? 4 times the height, right? So suppose you have 2 mine shafts, right? One rock falls and hits the ground in 5 seconds. The other takes 10 seconds. Ooh, that's twice the time to hit the bottom. That's 5 seconds versus 10 seconds. That's double the time, isn't it? Right? How deep is the deep mine shaft compared to the shallow mine shaft? 4 times the depth. Right, you could run the numbers too. Right, 10. Let's do 10 seconds. What's 10 squared? Be 100. And then half of 10 is 5. Put it all together, it could be 500. Right? What's 500 meters compared to the original 125 meters? Yep, that's 4 times the distance. Sure is. Okay. All right, you guys good on Paul Hewitt? That's good. All right, let's flip over to you guys' posters. All right, so of course, I gave you guys the thumbnail notes versions. Oh, if you guys have your notebooks out, then well, a couple of ways that this could be good. Anything you see, if you write something down, helps your brain process it a little bit better. Also, later on today, I've got some graphs. I'm going to throw some empty graphs on the board, like some axes, and I'm going to throw you some scenarios and see can you draw this or that graph. Right, you guys can get it. If you don't have your notebook with you today, then you guys see a couple of stools in the middle of the room. They got stacks of paper on them, copy paper. Right, so if you need paper, there's some paper out there. All right, so while you guys get that, we're good. Get you guys rolling. All right, so let's start off with variables and units. All right, so guys, remember in this class, you almost never see any naked numbers. Right, any number you see in this class, it's going to have a unit attached to it, and it's going to represent some variable. So how about the top line here? You can say x equals 3 meters, for example. So distance equals 3 meters, something like that. Okay? You don't just want to write down the number 3. It's like 3. What does that refer to? 3 what? Right? And then if you say x equals 3, right, even that's kind of ambiguous. We're talking about 3 centimeters, 3 meters, 3 kilometers. Right? So you got to have a unit, right? And then even if you just write that down, like 3 meters, even that could be ambiguous because what are you talking about? Are you talking about a height? Are you talking about a radial distance? Are you talking about a length? Right? So you got to have all of it. Like x equals 3 meters, something like that, right? I'm saying unit could be meters, but it could also be centimeters, could be kilometers, different ways to do it. If you see L in this class, capital or lowercase, I'm talking about some length that could also be measured in meters, centimeters, kilometers, and so on. Okay? If you see R, talking about a radial distance. Yeah, you guys remember last week, you were measuring different radial sizes of different circles. Okay? I tried to use capital R for a fixed radius and lowercase r for a variable radius, although I'm not 100% consistent on that. So try to do that though. Okay. Actually, I don't even know why I put that on linear motion because you guys aren't going to deal with radius for a few weeks anyway. Right? We're not going to go around curves for a while. Right? If you see H or Y, talk about usually I reserve those for specifically a vertical displacement, a height or a vertical displacement. Yeah. Okay. So these are all different types of displacements or distances. Right? All right. T as a variable can be time. I'll usually use lowercase t. If you use capital T, I'll tend to reserve that for like a time period. Right? Give like one lap around a track or something like that. Right. And we're going to quantify that in seconds. So you might say the time elapsed, lowercase t equals 3 seconds. Lowercase v, that comes from the word velocity. So you can think like how fast, right? Sometimes I'll use that for speed also, speed or velocity. And we're going to quantify meters per second, right? You could also think miles per hour. It's the same concept, some kind of distance per time unit, right? So in this class, meters per second, we're going to tend to use. Maybe we used centimeters per second last week, right? Something like that. What's the difference between speed and velocity? Because so speed is just how fast you're going. If you're in a car, the speedometer points to some number, that's your speed, boom, right? All right. Velocity is speed, but also direction is either specified or implied. Okay? Okay, so that might seem kind of like trivial now, but that'll make more importance later on in class. I'll give you an example right here. Right? You guys remember how acceleration is something you can feel? Acceleration is something you can feel, right? Right? It's okay. Well, gas pedal and brake. That way you can speed up or slow down. Now, that would be changing your speed or your velocity. Okay? But can you guys think of a way, maybe in a car, that you can change your velocity but have constant speed? How can you do that? How can you change your velocity but have constant speed? You do what? How about steering wheel? How about go around a curve? Right? Here's why. Because that speedometer needle might be pointing at a constant, like 30 miles an hour, 30 miles an hour, 30 miles an hour. Right? But your direction is changing, and you can definitely feel that. Right? So okay, so that means your velocity is changing. There's an acceleration involved. There's a force involved. All right, so you guys good with that? All right, let's throw some subscripts on these V's. I tend to use this not subscript V naught for initial velocity. Yeah. So if you throw something, it will have an initial velocity. Last week, you guys released the cars from rest, those Hot Wheels cars. So initial velocity was 0 for that scenario. Anything dropped, released from rest. Right. Some textbooks, some instructors use V sub I. Okay, so if you see that, right, okay, and that'll be in meters per second, right, or miles per hour, or kilometers per second, or centimeters per second. Just gave you one. Okay. If you see V sub F, we're talking about so final velocity. That could be the velocity at the end of an interval. Right. Last week, your guys' car is rolling down the incline. Do you guys think that between the initial point and the final point, between the top of the track and the bottom of the track, do you guys think it had like a bajillion different velocities all along? Because it was constantly speeding up. It was always changing its speed. Okay? But for a lot of these equations, we're going to break out some equations and solve equations. If you just know the beginning velocity and the end velocity and one other kinematic value, you can solve all kinds of stuff. So if you know the beginning velocity, end velocity, and how much time, you can solve for how much distance and what was the acceleration. Right? There's enough information there. All you need to know is, beginning velocity, end velocity. All right, acceleration. Okay, so lowercase a could be acceleration as a variable and quantify meters per second squared. And you guys remember what that means? That means you're changing some number of meters per second every passing second. meters per second per second. That's what meters per second squared is, right? So you're like speeding up or slowing down at some rate, right? Right. And then a really common acceleration is lowercase g. That could be acceleration due to gravity, like a gravity field, right? And on Earth, right? You guys remember that number is how much on Earth? Lowercase g? Yeah, 10 meters per second squared. Yeah, there you go, 10 meters per second squared. Right? More precisely, 9.8. I'll tend to use 10 meters per second squared, right? By the way, it's also about 32 feet per second squared, but I don't think I'm ever really going to use that in here, but FYI. All right, so 10 meters per second squared, gravity field on Earth, right? Now, if you go to Mars, that's now you got a different number. Okay? You guys got on variables and units, right? Right, so say G equals 10 meters per second squared, right? Variable equals number unit, like that. All right, you guys had, here, let's look at some of these graphs. This is a recap from last week. We did almost all these graphs last week. Let's start with mass versus time. Okay, so while you guys got your notes out, let's get practice. Go ahead and let's do mass versus time. Okay. On the vertical axis, put mass in kilograms. On the horizontal axis, put time in seconds, right? Just like I have it there. I want you guys to draw that graph. I've got the animation ready to go. When I click the next thing, it's going to put the graph in there. It's going to do it. Right? But I want to see if you guys either A, remember this, or B, can you sort of reason this out? Wait, okay, I forget what that graph looked like, but I kind of remember the concept that came out of this. And therefore, I can reconstruct the graph because I understand the principle behind this. Right? Do you guys remember what that bottom middle graph looks like? One says mass versus time. What does that look like? Okay, so you could have like some set distance, the car is rolling down, and you're changing the mass of the car. You got light cars, you got medium cars, you got heavy cars. I'm walking around the room to see who's going to remember what does this graph look like. Okay, give you guys time, because I don't want to just give you the answer. But let's see. Can you guys get this first? If you can get it before I show you the answer, that's really true for a lot of these, then that's a good indication to all of us that you really like deeply understand this, right? So yeah, I got light cars, medium cars, heavy cars. Right? Because what was the result? What was the result of that? If you put a light car next to a heavy car and you roll it down the same incline, it's the same length, then which car wins the race? What was the answer? Does anybody remember? Here, show hands. Who thinks the light car wins the race? Who thinks the heavy car wins the race? Who says they tie? Yeah. Remember they tie? They tie? You guys remember that? Right. Well, what does that look like on this graph? Here, you guys ready for the answer? Here we go. Bam, that's the answer there. That was, you guys remember making that graph back on Friday? Did that? So here's what this means. If you have a tiny mass car, maybe down here, it takes, okay, so some amount of time to go, say 200 centimeters. Okay, maybe it took like, I don't know, 1.1 seconds or something, right? Then you strapped on some lab weights, taped on some lab weights, right? And that car took the exact same time, even though it was more mass. That's like a point right here. Then you tapped on some more mass, right? And then even a more massive car, but it was the same time. So it's the same time, regardless of the mass of the car. That's why it looks like that. Okay, that's that relationship. Right. Right. Next one. I'm going to kind of jump around here, but right, kind of a sort of a method to this madness here. Let's do x versus t. Let's do x in meters versus t in seconds. Or last week maybe it was x in centimeters versus t in seconds. That's okay too. Right, we got variable unit. Right, so you guys make that one x versus t. So distance versus time. What does that graph look like? Distance versus time for an accelerating situation? Parabola. That was bam. That was that right there. Right. Now, different scenarios might have different shape looking graphs, but yeah, car going down an incline, that's an accelerating situation. If you drop a ball off the Grand Canyon, that's an accelerating situation. That type graph. Parabola, x versus t. Right. Next one. Let's do v versus t. So velocity in meters per second versus time in seconds. What does that graph look like? Oh, sorry. Let's rewind. I forgot. I forgot. I was going to do this middle one. I forgot about that one. Right. Okay, so if x versus t looks like a parabola, if you do x versus t squared, now that looks like what? Yeah, linear. Okay, so we're back to linear. Okay, so let's do it. Right. The three most important graphs, I think, are the ones on the right. Right. So you guys see x versus t, v versus t, a versus t. Right. So now we're ready for velocity versus time. Okay. So like speed in meters per second is a function of time in seconds. Okay, so you let the car roll 1 second and then 2 seconds and then 3 seconds. it's going faster, faster, faster. And what exactly does that graph look like? That was that one right there, right? Right, a linear relationship, right? Right. In fact, you guys know equation for that. You guys know velocity starting from rest. The velocity it picks up to is equal to acceleration times time, right? So actually, I could say this too. I can say the slope of that line represents the acceleration. Just to fill you guys in, just to remind you guys where you guys have seen this. Right, that's here's x versus t, and here's the x versus t squared version, right? And here's the v versus t. Right? We just did those. Okay? So back over to the PowerPoint. All right, the next one we're going to do, I have not shown you guys yet. You guys see the one in the bottom right that says acceleration versus time? Okay, so acceleration could be in meters per second squared, and time could be in seconds. All right, now this one I have not shown you guys yet. Okay. But I think you might be able to figure this out. So it's going to be the same basic graph shape, whether it's the car going down the incline or you drop something off the Grand Canyon. The car rolling down the incline is just a slowed down version, but it's the same basic shape. Okay. What do you guys think acceleration versus time is going to look like? Just going to figure this out. Acceleration versus time. Looking around to see if I see any correct versions. If you don't quite get it, that's all right, because again, I have not shown you guys this one yet. All right. I don't think anybody got it. I may have missed somebody, but here, it's going to be. Wait, how about this? How about this? I really want to lead you towards the answer if you can get this. Wait. Well, let's do pure free fall on Earth. Grand Canyon, drop of a ball. Oh, it's falling down the Grand Canyon. What was acceleration due to gravity on Earth? 10 meters per second squared, right? Suppose it's been falling for 1 second. No, we're ignoring air drag, right? Ignoring air drag. Suppose it's been falling for 1 second. Is it picking up 10 meters per second per second? Yeah. Suppose it's been falling for 2 seconds. Is it still picking up 10 meters per second per second? Yep. Suppose it's been falling for 3. It doesn't matter how much time it's been falling for. It's always picking up 10 meters per second in pure free fall, right? Right? And again, your car is just a slowed down version of that, right? So if it's always the same acceleration regardless of the time, what does that mean on a graph? Zip. There's the answer. There's the answer right there. Yeah, it's just a right. And in the case of pure free fall, 10 meters per second squared, 10 meters per second squared, 10 meters per second squared. It doesn't matter how long it's been falling for. It's going 10 meters per second. It's always picking up 10 meters per second per passing second. Right? Makes sense? Right. Now, again, these 3 graphs on the right are the most important ones they really want you to focus on. Distance versus time, velocity versus time, acceleration versus time. Turns out that these 3 are related to each other. Like if you know any one of these, you can kind of figure out what the other 2 look like. Right? I'm sort of locked in place for some given scenario. Yeah. Right? That's good. All right. These last 2, yeah. These last I'm going to less focus on, but maybe it's good to know these, right? They'll show up sort of in the equations. Right? Do you guys remember velocity versus distance, what that one looks like? It's a little bit different. Who remembers? You guys remember it was like a square root type? You guys remember that? Okay. And then, then if you square the v and plot that versus x, okay, so again, all those graphs we did back on Friday, except for acceleration versus time. That one's a new one, acceleration versus time. Okay. I'm zipping along a little faster, but you guys know this whole presentation and all the ones I'm going to do in the future. You guys remember you can download these on Google Classroom, right? I think I put it under a file called textbooks. I put a bunch of textbooks there, including this whole thing. Okay, you guys got this. All right, next slide. All right. We're gonna do the slide. We're gonna do the slide, and when we finish this one, this will be a pause point. Oh, hey, look at those 3 graphs on the right: distance versus time, velocity versus time, acceleration versus time. I'm gonna toggle back and forth. Let me go back. Hey, x versus t, v versus t, a versus t. Toggle forward. X versus t, v versus t, a versus t. Look at that. This is the same set of graphs. Okay, guys, you're gonna see this over and over and over again, where I give you this exact set of graphs. X in meters versus time in seconds, v meters per second versus time in seconds, acceleration meters per second squared versus time in seconds. And I'll give you some different scenario. So I'll exchange out the scenarios. Here's the scenario for this one. Car drives at constant velocity. Go ahead and draw those 3 graphs in your notes. And I do want to, oh, good. We got 6 minutes. That's perfect. We got 6 minutes to do this. Okay. I want to see if you guys can get these 3 graphs before I reveal the answer. Okay. Now, guys, this is a different scenario from your lab. Your lab a few days back with the Hot Wheels car, that car was speeding up. That car was accelerating. This scenario here, look at that title. Car drives at constant velocity. Hey, is that like cruise control? Is that cruise control? Could you like be driving north toward Jacksonville, just constant 70 miles an hour, 70 miles an hour, 70 miles an hour? Right. Okay. Again, that's different from free fall. That's a different scenario. Can you figure out what those 3 graphs look like? Okay. Just give you guys a minute to get those axes drawn in your notes and yeah, try to draw the graphs. Draw the graphs. See if you get them right. If you guys can figure out what the graphs look like before I show them, that's a good indication to all of us that you know what you're doing. Okay. While you guys are thinking about that, let's look at these 3 formulas on the left side of the board. Maybe here, I'm gonna point with my mouse because maybe I'll show up on the video a little better. Okay. These 3 equations on the left side, they're really all the same equation. They're just algebra rearranged a little bit. Right, so let's do some examples. Guys, suppose you're driving north on I-95 and you drive 70 miles an hour. Okay, 70 miles an hour, there's your speed. And you do that for 3 hours. You guys got that? Right. Guys, how far have you driven? 70 miles an hour, and you do that for 3 hours. How far is that? Is that 210 miles? Right? You guys got that? If I go 70 miles an hour for 3 hours, I've gone 210 miles. Okay? Right. Now, how about this one on the bottom left? Suppose I'm driving along, kind of zoning out, you know, somebody, right? And then I look at my odometer. I'm like, whoa, I've just gone 210 miles. And well, I left 3 hours ago. I've been on the road 3 hours. I went 210 miles. I've been driving for 3 hours. What was my average speed? Is that 70 miles an hour? Right? 210 divided by 3, 70. And then miles per hour, gives you miles per hour. Right? Right, guys got that? Right, one more. All right, you guys see this one right here? Look at this one right here. Suppose I'm driving north on I-95. You guys know those big old green signs on the side of the road? It says Jacksonville is 210 miles away. Right, okay, so 210 miles to go to Jacksonville. I look at my speedometer. It says I'm going 70 miles an hour. How long is it going to take to get to Jacksonville? It's 210 miles away at 70 miles an hour. 3 hours. You guys see that? Right. So again, this is really the same equation, just written 3 different ways. Okay. You guys got that? Right. All right. I'm ready to see graphs. I'm gonna walk around the classroom, see who got these graphs correct. Who got the graphs? Which 3? Ooh, that one looks right. Okay, that one. Oh, and that one. All right. So of those, you got 3 graphs almost. All right, working on it. All right. How about 3 graphs in for yes. Ooh, almost. All right, so all right, see 3 graphs here. There's some little different thing. All right, so you got x in meters and time in seconds. It got for 3. Quite what I'm looking for. Just there. Oh, yes. And that 0 out there work. Yeah, that's it. All right. I think you guys are starting to get there. Right. So of course I want to show you guys the answers, but have you guys think about it ahead of time. Right. I think once you see it, you're like, okay, I think that makes sense. But here we go. Right. I'm going to start with the middle one. I usually do that. I usually start with the middle one and branch out. So it says, so you're going, here's the story. You're going 70 miles an hour. 10 minutes later, you're going 70 miles an hour. 10 minutes later, you're going 70 miles an hour. 10 minutes later, you're always going 70 miles an hour. Right? Regardless of how much time's passed. Bam. There's the V versus T. There's your velocity versus time. You guys see it's constant velocity? Hey, that was the title of the scenario. Constant velocity. Hence, velocity is constant. Look at that. It doesn't matter how much time has passed. You're always going 70 miles an hour. Right? That's it? Right. From there, if you know that graph, you can figure out the other 2. Right? Okay? Right. So let's go to distance versus time. Right? Okay, so I'm going to start home base at like 0.0. Technically, you don't have to, but I'm going to do it. So 0, 0 can be a point, right? Then after 1 hour, I picked up 70 miles. Then after another hour, I pick up another 70 miles. Then after another hour, I pick up another 70 miles. What shape graph is that going to make? That's linear. Bam. Right? Actually, for any constant velocity on an x versus t, it looks like that. Okay. Again, this is different from your lab back on Friday. These graphs look different. Right? But constant velocity, it's like this. Right? All right, one graph to go. Acceleration versus time. Again, constant velocity. Guys, if you're constant velocity, what does it feel like inside the car? Suppose your friend's driving the car and you're blindfolded. Does it feel in that car a lot like just sitting in this room, like you're at rest? It sure does, because you're not doing what? You're not accelerating. You're not accelerating, right? Because you're not speeding up or slowing down. Guys, if you have zero acceleration, what does that look like on a graph? Zoop. I bet it looks just like that. Right? Zero acceleration. Again, this is for the scenario. This all pertains to the scenario constant velocity. Right, guys got that? All right, one last detail here is these three graphs are related. So the slope of x versus t, the rate change of distance versus time, is velocity. And the accumulated velocity versus time, like if you know you're driving some speed for some time, the area under that curve, in this case happens to be a rectangle, can tell you your displacement, how far you've gone. All right, and that is our perfect pause point right there. All right, so you guys have a great afternoon, and we'll pick up the story tomorrow.